Hello everyone, in this video we will find the shortest path with a little help from Dijkstra. So what is a weighted graph? In a weighted graph we have edges and every edge has some value associated with them, which are also called weights. So the weight of an edge usually represent the cost or distance between two nodes. So for example, from D to C we have a weight of 1 and A to B we have a weight of 3. That is a cost or distance. It can also represent the capacity that can be transported between two nodes. Now, in this graph, what is the shortest path from A to B? Now, if we're taking the route from node A to C and then C to B, it will cost us 2 plus 1, that is 3. Even though it may intuitively seem like the longer path, taking the route from A to C to B, but it is actually the shortest path from node A to B. Now, in this graph, there are many possible paths. We have a source A and we want to reach to node E. And as you may see, there are many possible paths that will allow us to reach node E from node A. One possible way is A to C, C to D, D to E. The next path may be A to B, B to D, D to E. And the next may be A to B, B to E directly. But what is the shortest path from A to E with the minimum cost? So we can use Dijkstra algorithm, which will help us to find the shortest path between two nodes. It will allow us to find the shortest path between from node A to E. With the help of Dijkstra algorithm, we can find easily. Dijkstra algorithm can be used to determine the shortest path from one node. One node will be the source node to every other node. For example, if we run Dijkstra algorithm, at the end we will get shortest distance from A to C, shortest distance from A to B, A to D, A to E. We will get the shortest path from one node, that is A, to every other node within the same graph data structure. This means that the shortest path between any two nodes can be saved and look up later. It will help us to find minimum distance between two nodes. Now we will see a running example of Dijkstra algorithm. We will make a table. In this table, we will write down all the vertex. We will write the shortest distance from A. A we are taking as source node, and we will make a column for previous vertex. When we start Dijkstra algorithm, we don't even know if all the other vertices are reachable. So the shortest distance from A to every other node we will mark as infinity. However, we do know the shortest distance of one node, that is of A. Since we are already at A, our start vertex, the shortest distance is 0. Once we have initialized our table, we will need to start visiting vertices from our start vertex A. A simple way to keep track of which nodes we have visited or haven't visited is within the two arrays. We can make our array for visited and unvisited, and we can put our vertices one by one. So at the end, all vertices will be in the visited set. Initially, all the vertices are in unvisited set. Now, from the table, we will visit the vertex with the smallest cost, and we can see A have a smallest cost. So we will make A as a current vertex. Examine its neighboring nodes and calculate the distance to them from the vertices we are visiting. So from node A, we will see the unvisited vertices. From A, we have C, which is unvisited. We have B, which is also unvisited. So we can compute the distance from A to C and A to B. So A to B distance will be 7 and distance to C will be 0 plus 3, that is 3. If we calculated distance is less than our currently known shortest distance, we update the shortest distance from these vertices. So for node B, and our calculated distance is actually less than our currently known shortest distance. So we will update our table value for these node shortest distances. We will also add A as the previous vertex. So we will write down the values and we will write the previous vertex here. Now from the table, we will see the next vertex which have the smallest distance. As we can see, we will next head over to vertex C. Remember, we need to visit a node with the smallest known cost. Since C's cost is the smallest of our unvisited nodes, that's what we'll check next. So, as we can see, 2 out of 3 of C's neighbors are unvisited. That is B, B, and D. A is visited. So we will check the shortest path from the vertex via C. So from distance from B will be distance of C and distance of C to B. That is 3 plus 1. That is 4. Now similarly, we will compute the distance of C to D. Distance to D will be distance of C plus distance of C to D. That is 2. 3 plus 2, that is 5. Notice that the shortest to B via node C is actually 4. This is shorter than the currently known shortest distance in our table, which is 7. We can update our shortest distance previous vertex value for B since we found a better path. So what we will do, we will update the value 4 and we will change it to B, and we will mark C as a visited vertex. Now again, since node B is unvisited vertex with the smallest cost, currently we visit the next, we will mark B as a current vertex. We check its unvisited neighbors and calculate their smallest distance from the start via node B. So distance to E now will be distance of B plus the weight from B to E. So B to E is 6. So B to E is 6. So we will write 4 plus 6, that is 10. How did we get these numbers? So the shortest known distance from start to B and the cost from node B to E is 6. So 10 is the shortest known distance to E from the starting vertex. So we will update the value as 10 here, and we will write the previous vertex as B, and we will mark B as a visited vertex. We will repeat the same process until we reach all the vertices. Now, of the remaining unvisited nodes, D has the lowest cost now. So our current vertex will be D. Since only one of D's neighbors is unvisited, that is the one we will examine. So to distance to E will be 5 plus 4, that is 9. Distance of D plus distance from D to E is 4. That is 5 plus 4 is 9. Since we have found a shortest path to E, we will update its row in the table. We will update this value 9 here, and we will update the previous vertex, that is D here, and we will mark D as a visited vertex now. The only node left to visit is E. However, all of its neighbors have already been visited, so there's nothing for us to examine or update here. So we will simply mark E as a visited vertex. Now the Dijkstra algorithm, as we said earlier, it gives us the shortest path from our starting node, that is from node A. It gives the distance to every single reachable node. We wanted initially to find the shortest path from A to E, but this table allows up all possible shortest paths. So from node A to E with a distance of minimum 9, and we can reach from A to B with a distance minimum 4, A to C distance minimum 3, A to D distance minimum 5. We can reduce a shortest path by following previous vertex of any node back up to the trees. Now, what is the path we need to follow to go from A to E? We can retrace a shortest path by following the previous vertex column of any node back up to the street. We can push each vertex onto a stack and then pop them off in order to construct our shortest path. Now, to find the shortest path from A to D, start at D. From D, we can go to B. We will write down D here, B here. From B, we can go to C. We will write B already there, C here. And from C, we can go to A. So we will stop here once we reach to the initial node. So the path we have to follow is A to C, C to B, B to D. Running Dijkstra algorithm once gives us all of the possible shortest path to the reachable node within a graph. Dijkstra algorithm is often implemented for path finding on a map. Dijkstra algorithm is considered to be a greedy algorithm because it picks up the vertex to which there is a shortest path currently known. That's what a greedy algorithm. It makes greedy choice. So Dijkstra algorithms make a greedy choice. So we visit n vertices and we relax maximum n into n vertices. So we can say the time complexity is n square. Now important points. Dijkstra algorithm works on both directed and undirected graph. Drawback: this algorithm will fail with the negative weights. Now, to work with negative weights, we have Bellman-Ford algorithm. In the next video, we will see how Bellman-Ford algorithm will improve the drawback of Dijkstra algorithm and how it works with negative weights. If you have any suggestion, any comment, how to improve this video, what to include, what should be the new video upon, so please write it down, please write a comment, and please subscribe and like. Thank you.